I don't know if I can express how important osmotic pressure is to microbiology. We preserve food using this knowledge. You have heard of salted meats or sugar-cured hams. Why don't jellies and jams have stuff growing in them if they're sitting on the countertop? It's because of the high sugar, the high osmotic pressure. These have a lot of solutes in there, and it causes the water to come out of the specimen. So you remember from freshman biology, hypertonic, hypotonic, and isotonic situations. Well, this applies especially to bacteria, so I want you to spend a little time thinking about it. The osmotic pressure is going to be a lot of stress on the bacteria. The bacteria need water to survive. And for every molecule of sugar or salt that they have taken up in their cytoplasm, it pushes basically a molecule of water out. So what you have is a balance. I can't have too much sugar inside that's in free form, individual glucose molecules. So they have to store it in the forms of starch or glycogen or long polymers. Because here's a really funny trick about chemistry. A single molecule of glucose has an osmotic pressure of 1. A disaccharide containing 2 sugars has an osmotic pressure of 1. A trisaccharide with 3 sugars has an osmotic pressure of 1. A billion glucoses in a long chain would have an osmotic pressure of 1. So it's more efficient for the bacteria to store their energy sources as long chains of starches or sugars than it is for them to store them as individual subunits. So they have to put them in these long chains, and then as they need them, they break off one individual bite at a time. There are different kinds of bacteria that have evolved to handle different concentrations. You have your normal growth of bacteria that can't tolerate high osmotic pressures. Even on us, we have salt on our skin, and that's the reason we sweat sodium chloride, is it inhibits the growth of a lot of bacteria. It does not inhibit a lot of staphylococci. It doesn't inhibit some streptococci. But for the most part, the salt concentration in our sweat inhibits bacterial growth. All right. So let's look at halophiles. They tolerate high osmotic pressure. Then you have extremophiles, and by high osmotic pressure, I'm thinking up to about 10%. Extreme halophiles can handle up to about 30% sodium chloride. So you find them growing in like salt lakes, in areas like that. And then you have some facultative halophiles who don't need the high salt, but they can tolerate it because they have mechanisms for getting rid of the excess sodium chloride or salts that are in their environment. This is also the reason we have one organism called Deinococcus radiodurans that can withstand high concentrations of radiation. 1,000 times the amount of radiation that would be required to kill a human. These puppies still keep going. Deinococcus can handle it. It's because Deinococcus can handle high salts. Remember, when you dehydrate and you pull all of the water molecules away from DNA, it has a tendency to break. So a halophile has learned ways of repairing damaged DNA. So they tend to be a little more resistant to the radiation that's out there. So it's just really interesting, and it's something that you should think about and understand, not just memorize.